Recording, share my screen, and to the quiz. I don't know about everybody, all of you, but to me, this kind of thing seems like a real pain in the butt. And so we're gonna do something a little bit different for this quiz. Everybody can just at the top up here, put yourself as 4-4 for now, and everybody gets full credits. We're gonna talk about, as we're going through, talk about the answers to this quiz problem. We're gonna talk about the real way that people go about doing this sort of counting thing in practice now. That everything that you just did is how people did this problem in the 1960s when computers were first being invented and we didn't have the appropriate supporting math to make this these problems easier. So I don't know. In some sense, you're welcome. You get full credit. In some sense, I apologize for making you go through all of that. But it will hopefully make you appreciate the stuff that we're going to talk about next and why we do it. And you will see that the math that we're going to talk about next to do this is going to be significantly more complicated in some sense because it's like much higher level math. But it's going to be much, much simpler in the sense that you can actually do it in your head and you can do it for very, very complicated programs. All of these programs are very simple programs that even if you, I don't know, maybe made an arithmetic mistake somewhere, you still probably had a good sense of what the program was doing. Yeah. So nobody does this counting like this since the 1960s. Instead, we have this this thing called big O or theta or omega notation. And we're going to go over the quiz using this. Before we actually get into the details of the math here, I want to just highlight that almost all resources that you will find online are wrong about this subject. So the reason most things are wrong about this subject is just because most things on the internet are wrong in general. They're not written by experts. If you look at things that are written by experts, for example, Wikipedia is a great source on this. That's great, but if you're looking at like random blog posts that come up on Google searches or like explanations for technical interviews, almost always going to have the wrong information here. So almost all information online is wrong. And so if you are looking for supplemental like material besides the lectures to follow along with this, see other resources, the textbook is good. They don't go into quite as much detail as we're going to go into. Otherwise, Wikipedia. Textbook and Wikipedia are safe resources to use, and you won't get misled if you use either of those resources. We're going to be going through this in a very technical way that is more technical than most data structures class go through this material. The reason for that is because I found that so the more technical explanations are required for classes after this. And so most or many classes just skip the technical stuff until later when it's needed more rigorously and do some sort of like high level hand wavy thing at this point. I find that just confuses people. So we're going straight into the full technical details of everything. Any questions at a high level before we get started with the technical material? Yes.
So when you're saying that most of the like technical related you just mean that it's using definition figure instead of like that definition, or is it just like outright saying like?
Yeah. So the question is are things wrong online because it's a difference between industry and academia? And the answer is no. That people who are like at say Google, who've been working there for a long time, well-paid engineers, really know what they're doing. Even if they've like even never been to college, they know the formal proper things about Big O notation. The reason almost all information online is wrong is just because a lot of people are writing about this without knowing what they're talking about. And so people will talk about what they think interview preparation should look like when they have never worked at a company like Google, when they've never properly taken CS courses. And so, yeah, I might be overstating things about almost all information online is wrong, but every semester I have somebody who has found a resource online that you think is a good one, that has some sort of helpful information for you, and they show it to me, and severely misled them on things. So I just, if you are looking for other resources, these are the two things that are safe. Other things, potentially incorrect. And I'll highlight some of the, when we get to the incorrect things, I'll highlight what those are. Okay, so on this first problem, we'll first just do it how we talked about before, where we have this n equals 4. So all of our for loops have 4 different things that they do inside of them. And I think I probably wrote the number 4 down over here. And then we multiplied all those things together. 4 cubed gives us 64. And if we were somehow to change this value of n to say like n equals 8, then we'd have to redo this problem for our new value of n and redo all the math. A slightly more general approach that we can do is that instead of doing the substitutions first, instead of replacing all these n values first, we can come up with a general formula that's based on n. And in this case, if I have 3 for loops all nested going one inside of the other, then my general formula is going to be n cubed is what count is going to be equal to down here. And so if I plug in 4 for n cubed, then I would get the 64. If I were to plug in 8, then I would get 512, I believe. This procedure right here is the key thing that we're going to do differently at first. So write out formulas. In terms of the n. And this formula up here, relatively straightforward. Let's go on to the next formula. Here the formula is getting a little bit more complicated. So on this first for loop right here, the number of times that it's going to go through is just n times 1024. This second for loop, I'll do it in a different color so that it's clear what I'm highlighting here. That green box right here, the inner part, this part right here, that'll happen n times. And then this part right here will happen 1. We'll have n plus 1 inside of this outer for loop. In green, n plus 1 times n. And if you were to substitute in your values for n, you'd see that that should hopefully get you the same numbers. And then this last one down here, the simplest one right here, that is just n by itself. And if we add all these things together, then we get the, so that'll simplify to n squared plus n. Add it all together, we get n squared plus 1024 plus 1 is 1026 times n. And that's our general formula down here. Usually when we're doing these sorts of counting operations, what we care about is the reason we're doing these counting operations is we want to know how many operations the computer is going to run. And by counting those number of operations, we can have an estimate of how long our program is going to take to run. And when we care about how long a program is going to take to run, there's two things that we care about. I'll write them out. Two things we care about. The first thing is, like, if the input to our program is really, really small, then the program's going to run fast no matter what. If the in value is small, it sort of doesn't matter which one of these algorithms that we're using. The count is going to be very small. The program will run fast. So what we really care about is we care about when n is large. And exactly what large means will vary from like application to application. Yeah, so we'll talk more about this later, exactly what we mean by that. And the second thing that we care about is like, I don't know, predicting if a program is going to take 10 minutes or an hour, that's useful. But if we have to run the program no matter what, we have to run some program, we don't necessarily care in advance exactly how long it's going to take. Instead, what we care about is which program is going to be faster. Do I think that the program in problem 2 is going to be faster, or do I think that the program in problem 1 is going to be faster? And so what we care about is not the actual like absolute speed of programs, but the relative speed of programs. The relative speed of programs, or the comparison between two programs. In this case, the comparison of the count values. And this big O notation is going to give us a good tool for being able to do this. We're going to pause talking about the problems on this quiz now and move over to the big O notation notes. We're going to talk about this formal definition of the big O notation. We're going to work through a bunch of examples, and then we're going to take this back over to the quiz problems and see how this relates to the quiz problems. The definition up here is a little bit abstract. This is the definition taken from Wikipedia. There are a couple of other equivalent definitions, but this one's the easiest to work with. Again, the definition, very abstract, hard just to look at it and see what's going on, but we'll walk through these examples, and I think the examples will make it clear. So if we have two functions, f and g, so here are our two functions, f of x is just x, g of x is x squared, then there are three things that we might want to say about them. Either that f is theta of g, or it's omega of g, or it's O of g. And so we're going to work through each of these cases on these examples to get an intuitive sense of what this means. In all three of these cases, we have this limit as x goes to infinity. So if I just make this fraction over here, so f of x over g of x is x over x squared. And simplifying that, we get 1 over x. And if I take the limit of this whole thing as x goes to infinity, then as this goes to infinity, the denominator gets really, really big. The numerator stays the same. So that ends up being equal to just 0, goes down to 0. If we look at our cases up here in the case 1, 2, and 3, then this 0 value right here is less than infinity. So we can say that f equals O of g. Here we say f equals O of g, or equivalently, x equals O of x squared. If we look at this step 2 right here, this case 2, then it says f of x or over g of x greater than 0, then we say f equals omega of g. In this case, 0 is not greater than 0, it's equal to 0, so we cannot say that f is equal to omega of g. And then theta of g means that both f equals O of g and f equals omega of g. So we can't say this, but because we can't say this. So the only thing that we can say about these two functions is that f equals O of g, or equivalently x equals O of x squared. The intuition that you should have about this O notation, this O right here, is that O is kind of like less than or equal to. That this is basically meaning that x is less than or equal to x squared. It's not exactly like x is less than or equal to x squared, because I can come up with some x values like 0.1, where this equation down here is not true. But this equation will be true for the x values that we care about, which are the large x values. If, yeah, so it's all very abstract still at this point. We're going to keep working through these examples, keep seeing more of, more of these examples, and then we'll go back to the application and the counting to compare about which of those algorithms is going to be faster, or which of them is going to have the largest and smallest count values at the end. Before we go to the next example, though, any questions about this example? Yes. What do I mean by this? Yeah. So when I say f equals O of g, all this means is that the limit as x goes to infinity of f over g is less than infinity. So the equal sign over here is not, it's doing something a little bit different than other equal signs that you've seen before. All it means, though, is that if you plug in the values for f and g, plug in very large values for x, then you're going to get something very small. Yeah, we'll see more examples here next. So this example 2, what happens if we reverse the f and the g values? So here in example 2, we'll do this one in blue. The limit as x goes to infinity, now it's g divided by f. Sorry. Still f divided by g, it's just the f and the g values are swapped from what they were up here. F divided by g, f is x squared, g is x, simplify, and you get that's equal to x. And when you take this limit as x goes to infinity, then this x right here just keeps going and going and going. It goes on forever. You get to the infinity value right here. And so we'll remember this infinity and come back up to our definitions. There we go, I can keep it all on one screen. Here, this part 1, the ratio right here is not less than infinity, so we cannot say that f is O of g. It is greater than 0, though, so we can say that f equals omega of g. F equals omega of g like that. And again, in order to be theta, we have to be able to say both O and omega. So here we cannot say theta. All we can say is that f equals omega of g. Again, substituting that in, x squared equals omega of x. And again, the way that you should think about the omega is as a greater than or equals to. So omega greater than or equals to. So like x squared greater than or equal to x. And again, we can't just use exactly greater than or equal to, because this is not in general true. If we were to plug in any value between 0 and 1, this equation would be false. But if you plug in any large value, then this equation becomes true. So the intuition behind the omega and the O is that for very, very large values, we're able to think of the thing on the left as less than or equal to the thing on the right, or the thing on the right as less than or equal to the thing on the left. So it's just like a more general version of less than or and equals and greater than or equals. The more general version becomes useful when we start getting more complicated formulas. So here, getting a little bit more complicated. Again, in order to do problem 3, limit x into infinity, f over g, x squared plus 2x plus 5 divided by x equals x plus 2 plus 5 divided by x, just simplifying, going from this step to this step, dividing each one of these terms by the x. And now when we substitute in the infinity, this term totally goes away because the x on the bottom goes to infinity, so this thing goes to 0. This will stay at a 2 over here. It doesn't depend on x, so it doesn't matter what we plug in. But this thing up out in front continues to go to infinity. So this whole thing will simplify to infinity. And now we have the still the same pattern that we had up here, that our expression went to infinity. And so we can say omega, but we can't say either O or theta. So here we can say that x squared plus 2x plus 5 is omega of x, or this is a lower bound of this thing over here. I'll stop for questions after one more example, because the next example will introduce this theta idea. So over here on number 4, again, always limit x into infinity of f divided by g equals x squared plus 2x plus 5 divided by x squared equals, and now simplifying, we get the 1 plus 2 over x plus 5 over x squared. That's an x squared down here. And so again, because the x's in the denominators down here, those will go away. And then we'll just get this whole expression is equal to 1. All of our previous expressions either evaluated to 0 or to infinity, but now we have something different. We have 1. And so if we come back up, look at our definition, 1 is less than infinity, so we can say that f equals O of g. 1 is greater than 0, so we can also say that f equals omega of g. And so we can say, in fact, that f equals theta of g, because it satisfies both this condition and this condition down here. So we say that, again, f equals theta of g, or actually substituting in the values, that x squared plus 2x plus 5 is equal to theta of x squared. And again, the theta, the way you should interpret it is that it's both less than or equal to and greater than or equal to, so it's basically equal. So this is basically like saying these two things are just equal. Not exactly equal, and in fact, these two equations will never be exactly equal, or almost never be exactly equal to each other, but they're almost equal to each other. They're going to be really, really close to each other. Any questions so far? Okay. The first major sort of mistake that a lot of internet things say online is they are talking about, they'll use the notation for big O. They'll say something, one equation is O of something else, and by that they'll mean that it's theta of something else. So this is the first common mistake that people make that you should not make, but very common for people to confuse O and theta. And I'm going to be hammering out throughout the rest of this semester all of the very subtle differences between O and theta when we're talking about different algorithms and why it's important to really understand that difference. At this point, you probably don't have necessarily good intuition about all of these things, but you should always be able to come back to this definition, just apply this ratio and the limits, and be able to determine what Greek letter you're going to use based on this test up here. Any questions at this point? Okay. The one, we'll do this example 2 next, and then we'll head back over to the to the quiz problems. What we're going to see over the coming semester is that we'll have a lot of terms and a lot of expressions that we're working with that follow one of these patterns up here. And it'll become very useful for you to just memorize which one of these things are bigger and less than of each other. And so I've just ordered all of these according to size, that all of these things follow this sort of relationship. And I'm being a little bit informal here, putting the less than or equals to, because that's really the intuition that you want to have. But when I'm putting less than or equal to here, what I'm really meaning is something like, whoops, n cubed equals O of 2 to the n. That's what this less than or equal to more formally means. And this one over here means that 1 equals O of log n, and so on. This notation's just a little bit more cumbersome than this one up here. And so people do informally use this less than or equal to, just with the implied knowledge that we're actually using the asymptotic notation, the big O notation or omega notation. And but this notation's a little bit more verbose. So when we chain things together, you'll see people using less than or equal to like this. I'm going to draw out these graphs now. And first, I want to compare, well, yeah, we'll just go from left to right. So the one value, just a constant straight line. I promise that's a straight line. That's the 1. And again, it's always going to be 1 no matter where you are on the x-axis. So anything that grows with in, this x-axis over here is in. Anything that grows within is going to be bigger than the 1 value. So then we have the log in, and the log in grows a little bit, but it's like really, really, really slow, something like that. That's log in. And then all of our, the linear functions come next. We have the x. There we go, something like that is x squared. And then x cubed growing a little bit faster than that. And one that, so yeah, these graphs you've probably seen before, the x log n graph, n log n graph like that, maybe not have seen before. That one's very, very close to the x graph, but just sitting slightly above it kind of the whole time. Basically looks like a straight line. If you weren't looking at it closely, you would think it's a straight line. And then the 2 to the n is just like exceptionally fast growing. It's going to look something like almost going straight up right away. Some of my equations down here use x, some use n. I guess I apologize for that on this picture right here, but people do go back and forth between all of these. Both n and x are very common for this. So you'll see people using those interchangeably. Again, if we look closely at the graph down here, all of these, it's pretty crazy down here about like what's going on and what's going to be bigger than what, but we're not going to be interested in this location down here. We're only going to be interested in the n is large case. And when n gets large, we get these clear separations between all these different functions. Any questions so far? Okay, let's switch back over to the quiz notes. And we'll start at the top up here. And what we're going to do is we're going to use the asymptotic notation. So that's the big O, omega, and theta to describe how this count variable is going to change as a function of n. So here we wrote in red what the count is equal to. And if we worked out the details of the math here, then n cubed, that would be just equal to theta n cubed. And hopefully that's a reasonably believable statement right here, that this thing over here is going to be equal to theta of n cubed. And then we're going to come down here to this next problem 2. And here we have a little bit more complicated of an equation. But this equation, if we were to work out the details of the math, we would see that we also, or that we get, instead of theta n cubed, we get theta of n squared, is a simpler version of this equation over here. In general, when we have these formulas that contain multiple terms, whichever one of these terms is the biggest asymptotically is going to be what it's going to be equal to in terms of theta notation. But so we have theta of n squared is what this bottom one comes out to be. And theta of n cubed is what this top one comes out to be. And we were just saying over here that the cubic is greater than the quadratic. And so that means that as n gets large, this program up here is going to take a lot more time to run than this program down here. I'll write that out in words. Problem 1 is theta n cubed. So it takes more time to run than problem 2. Which is theta n squared. What I'm going to do next, I'm going to switch over to a terminal, and we're going to actually demonstrate that, see that this top program will in fact take a lot longer to do things. It will do this count a lot more times. Before I do that though, any questions at this point? Yes. Yeah, so the question is, at what time value of n does the difference become significant? And this is a really great question. On this week's lab, you're going to be doing a bunch of experiments to see exactly for real world problems what the value of n starts having these differences. But it depends a lot on the different problems and how close the asymptotic relationships are. N cubed and n squared is a relatively large difference. So by n of 1,000, I would expect most algorithms would be showing pretty large differences here. When we get to problem 4, we'll say, well, I'll type in n equals 1,000, and we'll see that the computer won't finish that would take multiple years to run. So in that case, even up to like just n equals 2 or 3 shows really large differences. When we're talking about this asymptotic notation though, yeah, we're trying to not think about like the actual raw numbers of n, and just it's really large. In general, when you're working at a company, especially if it's like Google, Facebook size, they're working on data sets that are on the order of 10 to the 20 in terms of how many bytes they use up. And so they really care about the asymptotic stuff. Even much smaller companies though, the asymptotic performance is very critical for algorithms. Yes. So for the question is, where exactly is G and F coming from over here? And here, what I wrote in red, this is, I'll come back over here. Basically, I skipped all of the printed stuff and the stuff in that I wrote out, and just did this F equals theta of G part down here. So the thing to the left of the equals is always the F, and the thing that's inside the parentheses over here is always the G. Coming back over here, This is the F right here. And the G is that. And in this case, they're both the same thing. Coming down to problem 2. The question is, where did this come from? I just made it up. I'm just telling you that if we were to use n cubed and plug it into those formulas, then this statement right here would hold. And then, yeah, similarly down here, this whole thing is the F value. This is the G. I just made up the G. And my claim is that if we were to go through the algebra to do those fractions, then this statement would be true. But I just made it up because I know it will be true with this value. In general, the procedure to use to get a good guess about what to put inside of over here is just whatever is the term in the equation to the left that seems like it's the biggest term. So n squared seems bigger than n. And so if you try n squared, you'll see that it works. If you try n, you'll see that it's not going to be theta. It'll only be omega. Yes. Yeah, so the F that we're using right now is exactly what's coming from the code. And right now it's corresponding to the runtime of the code. In general, it can be any mathematical formula, but that's what the formula that we're using right now is coming from the code, how many count values we have. And the thing on the right is the simpler version that we're going to use to interpret it. Good question so far. Any other questions? Okay, I'm gonna come over to the terminal window and we'll just do some quick experiments to see how well this theory predicts what's actually going to happen when we run this code. And again, we said that the theory says that n cubed is bigger than n squared. And so this thing up here will take longer to run. It will have a bigger count value because it has a cubic over here instead of a quadratic. This is a little bit counterintuitive because if we just sort of look at how much code is there, there's many fewer lines of code in this problem 1 than there is in problem 2. Problem 2 looks more complicated, so it looks like it might take more time to run. But we'll see that that's not going to actually be the case. Inside of this quiz folder, I type ls right here, and you can see that I have these 4 problem statements. If I type cat on problem 1, this just contains the actual text of problem 1. And I'm going to do something just slightly different than what we've seen before to make the experiment here a little bit easier to run. But I'm going to use this command right here. And I'll just run this first and then explain what's going on. At this point in class, you're not responsible for knowing like why this is doing what it's doing. Later on in the semester, you'll be breaking down all of these different parts and fully understanding what's going on. But at this point, it's just enough to have an intuitive sense of what this command is going to do. Here, when I say n equals 4, that's going to say all of these n values. We're going to substitute in for 4 into where the $n is. The env subst command actually does that substitution. This is called an environment variable, and so this stands for substitute the environment variables. What it's substituting it into is the problem 1 up here. So I have 4 right here, so we plug in the 4s. If I change that to 8, then it plugs in the 8s. We're going to see one more shell feature here in a second, and that's called piping. We've seen something that looks like this before, print hello world, with the echo command. And if I do this, it just outputs this right here. The pipe operation allows me to take the output of this command and pass it directly to the input of another command without actually creating an intermediate file. So if I do this, that will take the output of the echo right here. And there's the output of the echo, pass that to the Python program. The pipe is equivalent to things that we've seen before, using the greater than sign to do test.py, and then Python 3 test.py. And what we're going to do is we're going to combine these two things together to make it really easy to try out different values of our in variable on our Python code. So if I press the up arrow to get back to this right here, this is the problem one statement as it's written in the quiz. Press the up arrow, pipe that to Python 3, and it tells me exactly what the actual count is for Python, or for running that Python code. So again, you don't have to grade your own quiz, but if you had the 64 there, that was the correct answer, and this right here is just running that problem. We'll do the same thing on problem 2 right here, and we'll run that and see what the right answer was. And so the right answer was 4,120. If you did get that, then good job with your arithmetic. But again, not graded, so doesn't matter if you missed that. What we're going to do, though, the reason I'm using these sort of slightly more esoteric commands is, well, two reasons. One is that I just want to get us more comfortable with seeing weird stuff going on in the shell, but bigger picture is that we're going to be able to change these numbers over here, make the in value large, and that we'll see as the in value gets large, suddenly problem 1 is going to give us much, much larger values for count than problem 2, and then it will stay that way forever. I'll do that experiment here in a second. Is there a question? That's correct. You don't have these files, so if you could follow along by typing that in really quick and creating them, but you don't need to. I would encourage you just to watch the numbers and try to pay attention, try to predict in your head, like roughly what's going to happen. So here, problem 1. Let's change that 4 value to an 8. And things get bigger as we change these values. The number gets bigger and bigger and bigger. And let's jump up all the way to, say, 30, and we get a really big number, 27,000 down here. If I change this to problem 2, similarly, the numbers are going to start off bigger than the other ones. But they'll keep getting bigger as I change these numbers. But the rate at which it's getting bigger is slowing down. It's not quite as big as the rate that the problem 1 was getting bigger. So here with n equals 30, problem 1 is still a little bit smaller than problem 2. But if let's jump it up a little bit more, 50 for problem 2. Adding that 20 there, we didn't quite double in size, up to 53,000, problem 1. Problem 1 now is way, way bigger than problem 2. Problem 1, way, way bigger than problem 2 at n equals 50. And if I change that to n equals 100, then the difference in size is even more pronounced, that now it's a whole factor of 10 bigger. So as this number gets bigger, we'll see that problem 1, this count is just going to keep getting bigger and bigger and bigger and bigger, much faster than problem 2. And that's what's predicted by this theta notation. That up here, it's again theta of n cubed. So that means for the large values of n, this is going to get a bigger number for us. Theta of n squared. For the large values of n, it's going to get a smaller number for us. And we don't usually care about the small values because if something's running in 10 milliseconds versus 100 milliseconds, who cares? But if I type in, let's see, so 200 now, problem 2, it's happening instantly. Problem 1, now it's not happening instantly anymore. We're having this delay here. Go up to 300, now it's going to have a huge delay right here, whereas problem 2, still instant. So once we get into the numbers that like actually matter for these problems, where the runtimes where the runtimes actually starts to matter, then we're having good predictive results from this asymptotic theta notation. Question, yes. So problem 1 and problem 2 are exactly the Python files from your quiz. Yeah. It's just a Python file. We're substituting in the in values over here for whatever this in value is. Again, so your lab this week will have you doing more of this, running more experiments on more complicated, more real-world problems to get more of an intuitive sense of how this asymptotic notation works. Yeah. Question is there any way for you to like automatically do this, automatically get your runtime evaluation? And the answer is no. It actually turns out to be mathematically impossible to have an algorithm that will look at code and predict how long it's going to take to run. There's a very famous problem called the halting problem, which says that you can't even predict whether a program is going to stop or not stop. And if you go on to take theoretical computer science classes, that would be the sort of thing that you would be talking about is why is that the case? And it turns out there are some programming languages where they don't allow you to do certain things because that makes you able to talk about the runtime and predict the runtime automatically. Python does not have those limitations. So in Python, you can't say anything without just actually running it. You'll find that in a couple of weeks, you'll have pretty good intuition about looking at code samples and figuring out, like, is this going to be a slow algorithm or a fast algorithm? Okay. So we're going to go on to the example or problem 3 down here, which is a little bit more complicated. And the reason it's more complicated, so everything is the same in problem 3 down here, except for this line right here. In this line right here, I snuck in this little I value right here. And so now when we're trying to figure out like how many times is this inner for loop going to run, the number of times this runs this for loop will iterate. So it's really the this line right here, line 9, how many times line 9 will run depends on I. So we can't actually say that that this thing right here, we can't say that this is not n squared. We can't say that it's equal to n squared because it's not equal to n squared because we're not starting at 0 each time. We're starting at some other number. So we can't actually find, there is a formula that we could use to try to figure this out in this case, but it's a complicated formula. And in general, there might not be formulas. So it'll be very hard to find exact formulas here. But what we can say, it's not equal to n squared, but it is less than or equal to n squared. So here, line 8 is not going to run exactly n squared times. Line 9 right here is not going to run exactly n squared times because of this I on line 8, but the number of times that will run is guaranteed to be less than or equal to n squared. It's guaranteed to be less than or equal to n squared because this I right here is only removing some of the values that we would run through otherwise and not adding anything else. So when I write out my formula, write out my f value, everything's going to be exactly the same up here. But instead of saying that f is exactly this thing right here, instead of saying it's exactly this is only an upper bound that I have on what the size of count will be. my n squared plus 1026 n is no longer exact. It's just an upper bound. And the O notation is what we should think of when we think of upper bounds. That we'll be able to say that this, our f, is less than or equal to this thing right here. So when I do the f over g, then I know that this is going to be less than or equal to n squared plus 1026 n. I'm still going to use for my g n squared divided by n squared. And this thing will be 1 plus 1026 divided by n. This thing will go to 0. So that's 1. And all I can say is that f over g is less than or equal to 1 because this is an upper bound over here. I don't have a lower bound yet, so I can't talk about the omega. I can't talk about the theta. All I can do is talk about the big O notation of this. And in this case, because it's less than infinity, we can say that f equals O of g. So that O of n squared, that this expression right here is O of n squared. But we can't say that, we can't yet say anything about like how guarantee that it will take that much time. All we can say is that it might take up to this much time. The key thing about this again, because I have the I right here at the very beginning, I'm starting not at 0, but at some number bigger than 0. So the number of times I run line 9 is going to be less than the number of times that I ran line 9 in the previous problem. This is the only difference between this problem and the previous problem. And so rather than trying to compute an exact formula for what the count value is going to be, I'm going to put this upper bound on what the count value is going to be. I know that the count value is going to be less on this problem than it was on the previous problem, again, because this I right here. And so I have f is now less than or equal to this thing instead of exactly equal to it. Substituting into my f over g, taking the limit as n goes to infinity. Write that out explicitly. N goes to infinity. We see that we can prove that it's less than or equal to 1. We can't say anything about whether it's greater than 0 at this point. And so all we can say is that f equals to O of g or O of n squared. So we have this upper bound guaranteeing that our runtime is not going to be too big, but we can't say anything that the runtime is going to definitely be small. Usually what we care about is these upper bounds, because with this upper bound over here, with this fact that I can say that f is no bigger than n squared, that means that when I come up and compare it to this first problem, n cubed over here is bigger than n squared. And down here on this problem, I can say that f is not bigger than n squared, so it definitely can't be n cubed. And so the runtime of this problem 3 is going to be less than the runtime of problem 1. I can say that with certainty, but I can't say anything about exactly how fast it's going to be. All I can say is that it's less than the runtime of problem 1. Any questions about that? Yes. So we can't say, well, it turns out we will be able to say a lower bound eventually, but all we can say is an upper bound. And by upper bound, what I mean is that we have a value that is, an upper bound means that we have something that we know we're lower than. So upper bound means that we can't go above the bound. This is the highest uppermost value that it can be. So the value that we have up here is the largest value that it can be. And that's what this less than or equal to is saying. Does that answer the question? Yeah, so the question is, here, if we're only talking about an upper bound, can we talk about a lower bound? And the answer is that yes, we can talk about a lower bound. We just haven't done that yet. For any of these things, we know that the lower bound is, an example of a lower bound is 0, because the program, the count value just starts off at 0 and we only possibly increment it. So 0 is a valid lower bound for this count value. We could also, just looking at this for loop and this for loop, come up with another lower bound if we wanted to. But the statements that we've worked through so far are just about the upper bound. In general, upper bounds are more useful than lower bounds, but there are times when you want to talk about lower bounds too. Good question. Yes. Yeah, so now the question is comparing problem 2 and problem 3. Let's take a look here. Let's go actually to the terminal and let's think about how problem 2 and problem 3 are going to behave in terms of the actual numbers they're giving us. So let's start with the n equals 4 value. This is again the answer right here to problem 2. And I'm gonna just rerun this with problem 3 and we'll see what the answer is. And you can see that like these numbers are really, really close together. Really, really close together. If I change this from 4 to say 40 for problem 3, 40 for problem 2, these numbers are still really, really close together. And no matter what numbers I select over here, these numbers are going to stay pretty close together. So technically, all that we can actually say is that problem 2 is theta of n squared right now, and problem 3 is O of n squared. But the intuition that should be giving you is that they are like, we should be thinking of them as the same thing. Good questions, yes. Yeah, this is a great question. So the question is, on the left-hand side of this whole little crooked line, I'm make myself less crooked. This thing on the left is what's matching the definitions, and this thing on the right is a 1. And if we come back to the definitions up here, a 1 is less than infinity, and a 1 is greater than 0. At this point, though, all we can say is that this expression right here, if we basically remove all of this stuff in the middle, then you get the limit as n goes to infinity of f over g is less than or equal to 1. And this thing in blue is the only thing that we have actually like shown at this point, that it's less than or equal to 1. We did get the number 1 at the end. 1 is greater than 0, but we don't know if like this thing over here is, yeah, all we have is this upper bound. All we can say is that f is less than or equal to this thing. We can't say that f is greater than or equal to something else, or that f is exactly equal to something. So because we have this less than right here that comes from this less than right here, when we go back to the formula, we can only this definition 1 is something that applies to us. Good question. Let's go on to the 4th problem from the quiz. And the 4th problem is very, very similar to the 3rd problem. It still has this I over here. The only difference, though, is now this line 11. Here, instead of in, we have 2 raised to the power of n. And if we work through the math again, that we'll get our f function. So up here at the top, n times 10, 24. Then this one, again, we can't find our exact formula, so I'll change this equals to a less than or equals and say plus n squared plus n. This expression corresponds to those 4 lines. This extra n right here is coming from that line right there. And then the very last of these 4 loops is plus a 2 to the n is how long it's going to take to run. And now I'm going to use as, if we use as a g value, the g equals 2 to the n, we'll see that that's the best that you can actually do at this point. And we would simplify this to f equals O of g equals O of 2 to the n. The important thing here is that this 2 to the n, is much, much larger than the n squared from the previous problem. And so even though this seems like a really innocuous change, a small change, very few like actual characters added here, just a 2 and 2 stars, most of the code is up here. We'll see that this is really going to dominate the runtime and make our count variable increase really, really fast. If I come back over to the terminal, and let's go back to n equals 4, we'll compare problem 3 and problem 4 now. Problem 4 is a much, much smaller value initially. And let's change this value to 10 right here, though. You can see it's growing pretty fast. And let's change it to 20. And we get this really, really big value down here, whereas problem 3 at 20 is much, much smaller, over 100 times smaller. Go back to problem 4, change that 20 to a 30, then it's not even gonna finish in time for class. It'll just sit here running forever, essentially. I'll press Control C to stop this. But with problem 3 at n equals 30, finishes very fast. So the intuition here is that this exponential 2 to the n is going to take a lot of time. Quadratic is like a medium amount of time. Cubic, also medium amount of time, but more than quadratic. And if we had something that was linear or less than linear, then it would be very fast. In this class, most of the algorithms that we see will be in the log n, and in log n range. Over the next 2 weeks, we're going to spend a lot of time really focusing in on these 3 runtime ranges and how fast they are. And then we'll see the ways to avoid being inside of these runtime ranges over here, ways to accidentally get into this really slow regime of computing, and how to avoid that. Any questions? Yes. Yeah, so the question is, how did I decide that g should be 2 to the n over here? And this is a little bit of an art that it takes some practice figuring out what's the best g value to pick when you're given an f function. The general rule of thumb is that when you have several terms inside of here, you should think about the term that is going to be the largest. So in this case, I knew that 2 to the n was going to be larger than these other things. And so that's what I selected for 2 to the n. We'll sometimes take trial and error to figure out just what the right g value is here. And again, as we go through this course, this is just our introduction to these concepts, getting us the most basic familiar with the definitions. We'll be doing this a lot more and having you actually selecting these g values, figuring out the runtimes for yourself. At this point, you don't have to worry about that. The main purpose of this lecture, what you want to make sure that you're comfortable with for Friday's lab, is this sort of hierarchy of functions, what's less than what, and just how do you apply these definitions to get a particular value. If you can do that, then you'll be all set for the lab, which will help make the stuff over here a little bit more concrete. Question is, do you have to hand in the quizzes? And the answer is no, you don't have to hand them in. If anybody else has any questions about anything, I'm happy to stay after class, get those questions answered, but that's it for today.